Hello everyone. This video, which is the first video of the chapter Continuity and Differentiability, I'll be introducing the concept of continuity. So let me explain the concept of continuity geometrically first. So if you consider the function f of x equal to x, if I draw the graph of this function, so you already know it is a straight line. And if you observe this graph, there are no breaks in this graph, or in other words, the graph can be drawn with a single without lifting the pen. If I draw the graph, I need not lift the pen, I can draw it in one stroke. So this is one graph where there is no break in the graph. So graph of f of x equals to x, if you consider it, it has no breaks. One can draw the graph of this without lifting the pen. Now if you consider another function, f of x is equals to 1 if for x less than 0, 2 if x is greater than or equal to 0. Now suppose we draw the graph of this one. It will be when we are coming from the left of 0, it is 1. So at 0 the function value changes. So if you are drawing this graph, the pen we have to lift at 0, or there is a break in this graph at 0. So there is a break for this particular graph at 0. So now one more function and its graph. F of x is equals to 1, x not equals to 0, 2 if x is equals to 0. So again, if you are coming from left of 0, when it reaches 0, the value of the function is 2. So at that particular point, there will be a hollow circle. So at 0 the value of the function is 2. So again there is a break at 0. To the left of 0 it is 1, to the right of 0 also it is 1, but at x is equals to 0 the value of the function is 2. So there is a break at x is equals to 0. So that is the geometrical meaning of continuity. A function f will be continuous at x is equals to c if there is no break in the graph of the function at the point c f of c. If there is no break in the graph of the function at the point c f of c, then we say that the function f will be continuous at x is equals to c. If there is a break, then the function is not continuous. And similarly, in an interval, function is said to be continuous if there is no break in the graph of the function in the entire interval. If in the entire interval there is no break in the graph of the function, then we say that the function is continuous in that particular interval. So this is the geometrical meaning of continuity. Now we'll define it using limits. So how we are, so let f be a real function, so real on a subset of real numbers. So we are defining a function on a subset of real numbers, and c be a point in the domain of f. C be a point in the domain of f. Then we say that f is continuous at c. F is continuous at a particular point c if limit extends to c f of x equal to f of c. Limit extends to c f of x equal to f of c. So when we say that limit, then it means that left hand limit and right hand limit. That means if the left hand limit, right hand limit, and the value of the function at c, value, these three should exist and should be equal to each other, then only we say that the function is continuous. That is, limit should exist means limit, left hand limit should be equal to right hand limit. That is, limit extends to c minus f of x should be equal to limit x tends to c plus f of x, and it should be equal to value of the function. If these three are equal, then only we say that f is said to be continuous at x is equals to c. If f is not continuous at c, then we say that f is discontinuous at c, and c is called a point of discontinuity of f. Point of discontinuity of f. So when you are asked to find continuity at a particular point, you have to check for left hand limit equal to right hand limit, and even if left hand limit and right hand limit are equal, that should be equal to value of the function at c. Now let us go back to the first example. So if you take any point on this function, the domain of this function, so this is a function defined from R to R. So if I take x is equals to 2, that is the point here, x is equals to 2. So if now I want to check whether it is continuous at x is equals to 2. So for that I have to see limit x tends to 2 f of x. So f of x is here x, so it will become limit x tends to 2 x, so that is equal to 2. Now here to the left and right of 2, the function has only one value, so if we take left hand limit and right hand limit, still you will be getting it as 2 only. So here we can directly find limit x tends to 2 x, that is equals to 2 f of 2. So after finding the limit, you have to find the value of the function at that particular point. So f of 2 is also 2. Now since limit x tends to 2 f of x equal to f of 2, f is continuous at x is equals to 2, continuous at x is equals to 2. So here since f of 2, this is one particular point I took, that is x 2 f of 2, so 2 comma 2, that is a point I took. So if since limit x tends to 2 f of x equals to f of 2, you can say that this function is continuous at x equal to 2. If you take any point, the similar way we can prove that it is continuous in the entire real number. So that means it is a it is continuous throughout its domain. Now for this example, so if I want to check continuity for this particular function, so that means I have to find out limit x tends to 0. Limit x tends to 0 f of x. I am checking continuity at x is equals to 0. So again to the left and right of 0, the function has two different values. So I have to find left hand limit, that is LHL. So LHL equals to limit x tends to 0 minus f of x. So that is equal to limit x tends to 0 minus f of x to the left of 0 is 1. So this limit will come as 1. To the left of 0 it is 1. And for finding right hand limit, limit x tends to 0 plus f of x. So it is equal to the right of 0, the value of the function is 2. So that means the limit is 2. So here left hand limit not equals to right hand limit. Left hand limit not equals to right hand limit. So that means the limit does not exist. Limit x tends to 0 f of x does not exist. This limit does not exist. So the function is, even if the limit does not exist, then that means the function is not continuous at x is equals to 0, or the function is discontinuous at x is equals to 0. So suppose I want to check continuity of this function at x is equals to 1. X is equals to 1. So that means I have to find limit x tends to 1 f of x. So to the left and right of 1, the function has only one value, that is 2. So limit x tends to 1, the value will be 2, so the limit of that will be 2. And f of 1 is also 2, x is greater than or equal to 0. So therefore limit x tends to 1, f of x equals to f of 1. So the function is continuous at x is equals to 1. Similarly, you can prove it is continuous at 2, 3, 4. So any value except 0, the function is continuous. That means the function has break at only 0. All other points the function is continuous. Again, coming back to the definition, to prove that a function is continuous at c, you have to check for the existence of limit x tends to c f of x. That is, when we are approaching c from the left as well as right, the value of the function, expected value of the function, and if it is equal to the value of the function at that particular point, that is f of c, then we say that the function is continuous at a particular point. If it is not continuous, then we can say that it is discontinuous at c, and c is called a point of discontinuity. Now if you are considering continuity in an interval, continuous in an open interval AB, so it should be continuous at every point in the interval. Then we say that the function is said to be continuous in an open interval AB. So if it is continuous at every point in the interval. For a closed interval, a function is said to be continuous in the closed interval AB if it should be continuous at every point in the open interval AB, and at the end point it should be limit x tends to a plus f of x should be f of a, and limit x tends to b minus f of x equals to f of b. So that is, if you are considering a closed interval AB, and if you are checking the continuity of this a particular function in this interval, so here it should be continuous at every point in the open interval AB, that is excluding a and b, and the right hand limit at x is equals to a f of x should be equal to f of a, right hand limit only, and left hand limit at b should be equal to f of b, because we are considering in this particular interval. Right hand limit at b will be outside this interval. Similarly, left hand limit at b will be left hand limit at a will be outside this interval. That's why we are checking right hand limit f of limit x tends to a plus f of x should be equal to f of a, and left hand limit x tends to b minus f of x equal to f of b. A real function next is a continuous function. A real function f is said to be continuous if it is continuous at every point in the domain of f. Every point in the domain of f. So for example, the first graph which we saw, f of x is equals to x. So this is a continuous function. So the graph will not have break in anywhere in its domain. So it is a continuous function. F of x is equals to x is a continuous function. So if the standard functions, you can easily prove that all are continuous. That is, f of x equals to x square, f of x is equals to sin x. All these from the graph itself we can say that these functions are continuous, because this does not have any break in the graph of the function anywhere, or it is continuous at every point in the domain of f. Geometrical meaning of continuity already I told. Function f will be continuous at x equals to c if there is no break in the graph of the function at that particular point. If there is a break, then it is discontinuous. in a particular interval the function is said to be continuous if there is no break in the graph of the function in the entire interval. So it's the same thing, only by using that only you can say that f of x equals to x square, f of sin x, f cos x, all these are continuous. A continuous function, it has no breaking anywhere in the graph of the function. Now the last part, discontinuity. So the function f will be discontinuous at a particular point x equal to a if any of the following case, in any of the following cases. So first case is that is limit are exist, limit left hand limit and right hand limit exist but are not equal. So this is we have seen in the second example, the limit left hand limit and right hand limit exist but are not equal. So this is the first case of discontinuity, that is left hand limit and right hand limit exist but are not equal. Now second case, limit exist, the limit will exist and are equal, that is left hand limit equal to right hand limit but not equal to f of a, but not equal to f of a, that we have seen in the third example, limit exists but it is not equal to f of a. So this is the second case of discontinuity. So first case, limit does not exist, left hand limit and right hand limit exist but are not equal, that is same as limit extends to a, f of x does not exist, limit extends to a, f of x does not exist. So here limit exists but not equal to f of a. So that means limit extends to a, f of x, this exists but it is not equal to f of a. And the third one is f of a is not defined, f of a is not defined at a particular value, that value also the function is discontinuous. So that's all in this video. I will do some examples in the regarding continuity in the next video. Thank you.